Good morning, champs. Today we are going to learn a second method for calculating member forces in a truss. Until now, we have used the method of joints. With that method, we isolate one joint at a time and gradually work our way through the structure. This works very well when we want to determine many or even all of the member forces. But what if we only want three specific member forces in a large truss? Do we really have to solve all the joints between us and those members? No. Instead, we can use what is called the method of sections. The basic idea is surprisingly simple. Instead of isolating a joint, we imagine cutting through the entire truss. The cut exposes the internal axial forces in the members that we cut. These member forces then become external forces on the free body diagram of the isolated section. For a planar structure, we have three independent equilibrium equations. We can use horizontal force equilibrium, vertical force equilibrium, and moment equilibrium. For this reason, we normally choose a section that passes through no more than three members with unknown forces. The section must also completely separate the truss into two parts. Once we have made the cut, we can analyze either side. Both sides give exactly the same member forces, so we normally choose whichever side produces the simpler free body diagram. Let's apply the method to the same truss we used in the previous lesson. This time, our horizontal load is 30 kilonewtons. The first vertical load is 15 kilonewtons, and the second vertical load is 25 kilonewtons. Each panel has a width and height of 1.5 meters. Suppose we only want the forces in members A, B, and D. Instead of solving the complete truss joint by joint, we draw a section that passes directly through these three members. Before using the section, however, we first need the support reactions. Horizontal equilibrium gives a horizontal reaction of 30 kilonewtons acting opposite to the applied horizontal load. Taking moments about the left support gives a vertical reaction of 23.75 kilonewtons at the right support. Vertical equilibrium then gives 16.25 kilonewtons at the left support. Now we make our section through members A, B, and D. The cut divides the truss into two separate parts. We could analyze either side, but the left side contains fewer forces, so we choose the left portion. At the cut, we draw the three unknown member forces. We initially assume that all three members are in tension, so the forces point away from the cut. If one of our final results is negative, we will know that the actual member force acts in the opposite direction and the member is in compression. Now comes the most useful part of the method of sections. Look at the lines of action of members B and D. They intersect at the upper right joint of our isolated section. If we take moments about this joint, both of these unknown forces disappear from the moment equation because their moment arms are zero. That leaves only member A together with the known support reactions. Taking moments about this joint and solving the equation gives 46.25 kilonewtons for member A. The result is positive, so our assumed tensile direction was correct. Member A is in tension. Next, we want member D. This time, look at members A and B. Their lines of action intersect at the lower left support joint. If we take moments about that point, both unknown forces disappear. The moment equation then contains only the horizontal external load and the force in member D. Solving it gives negative 30 kilonewtons. The negative sign tells us that our assumed tensile direction was incorrect. Member D is therefore in compression, with a magnitude of 30 kilonewtons. Only member B remains. Because the panel width and height are equal, the diagonal member forms an angle of 45 degrees. We resolve its force into horizontal and vertical components and use vertical force equilibrium. The vertical component of member B must balance the vertical support reaction. Solving the equation gives approximately negative 22.98 kilonewtons. Again, the negative sign means that the member is in compression. Our three results are therefore 46.25 kilonewtons in tension for member A, approximately 22.98 kilonewtons in compression for member B, and 30 kilonewtons in compression for member D. The important lesson is not the numerical result, it is how we chose our equations. First, calculate the support reactions, then decide which member forces you actually want. Make a section through no more than 3 unknown members and choose the easier side of the cut. After that, look for points where 2 unknown member forces intersect. Taking moments about such a point eliminates both forces immediately and allows the third member force to be determined directly. This is what makes the method of sections so powerful. The method of joints works through the truss joint by joint. The method of sections allows us to jump directly to the members we are interested in.